right, moving on up in the world today. We've started with sets and we're going to go to sequences and sums, or you'll hear them also called summations, or you'll even hear them called series. So let's remember a couple of vocabulary words here, right? Or not vocabulary words, but some basic definitions here. Two of them you haven't been exposed to yet. One of them you have, though, a set. So what is a set? Yeah, it's just a group of stuff, right? A collection of stuff. The key point, though, is that it's unordered, right? It's an unordered list, okay? A sequence is the same exact thing, except it's in order. That's the only difference. It's a group of stuff that's in order. So the set 1, 2, 3 could be represented as 3, 2, 1, or 2, 1, 3, or 3, 1, 2, and that's still the same set. But the sequence 1, 2, 3 can only be represented as 1, 2, 3, right? And then a summation. Any guesses what a summation might be? Yeah, it's a sequence that's been summed up, right? If you're familiar with sigma notation in calculus, that's basically what we're talking about, which we are going to look at that today, just in case you're not familiar with it. Okay, so it's just a sum of an ordered group of stuff. In other words, it's a sum of a sequence, okay? So the main focus today, we already know about sets. We spent the last couple lectures on that. The main focus today is on sequences, and we'll do a little bit about summations towards the end of the day today, okay? So here's a sequence, and this type of sequence, sequences and summations are also known as progressions. That's another term, that's an umbrella term that covers sequence and summation, progressions. This happens to be what's known as an arithmetic progression, okay? AP, that's the easier way to abbreviate that. So here's an example of a sequence, 1, 5, 9, ... What's the next number in the sequence? Why? How do we know that? Yeah, it's just increasing by 4, right? Is this some sort of trick where maybe it's going to increase by 5? Yeah, so generally speaking, when you're going to write out a sequence, you only need 3 digits for the pattern. Okay, this isn't one of these Mensa questions where like there's some weird pattern you're looking for, right? It's just simple. The pattern is obvious, and you're looking for a common difference. That's how you know it's an arithmetic progression. There's a common difference, and the common difference, as we saw, is 4. So if I wanted to have a different sequence that has maybe a different kind of progression, then maybe we need more digits to demonstrate the sequence. But again, the idea is it's supposed to be obvious. These are not meant to be mind games that you play with people, right? They're meant to be an obvious way to represent something specific. And so when you're dealing with a data structure or some sample data or something, or you have some sort of sequence, and we're going to talk about some famous sequences a little bit later, but you're just representing it in a clear, concise way, right? So how do we know? We talked about this already, that there's a common difference. So there's quite a few things that we're going to look at here dealing with the arithmetic progressions. Okay, the first thing I want to do, the idea here is I want to generalize this into a general formula to help us wrap our heads around it a little bit better. So we're going to use some variables, okay, to help us represent the pattern. And so we're going to use the letter A to represent the first term. So if you remember 1, 5, 9, in that particular scenario, A would equal 1, right? And the next term we're going to use, next variable I should say we're going to use is D for difference. Okay, you can use whatever variables you want, but these are pretty commonly used. So A for the first term, D for the difference. And then the other thing that's important to note is that A and D is an element of the set of real numbers. Okay? So we're going to use these to contrive, or not contrive, derive, big difference, to derive some formulas here that we can use to represent arithmetic progressions. One way to represent it is just write the numbers out like we just did, 1, 5, 9, ... That's one way to do it. But there are other ways to do it, and you can do it using a formula. And there's functions in several different ways, okay? So let's keep this sequence in mind as we're doing this, to just sort of keep that in the back of our head. And the first thing we can look at here is just basically looking at the values in variable form, or in sort of a pattern. So what if I were to write 1, 5, 9, but I wanted to use these variables A and D, what could I write? What would be the first term?
1.
Well, yeah, but using the variables. A, right? That's sort of a given already, right? So A. What would be the second term? It would be a plus d, right? You see that? Because d is the difference between everything, and that's a given number, in this case 4. So wouldn't the second term be the first term plus the difference 4, right? Very good. Okay, what would the third term be? A plus 2d, right? It's the difference 2 times, right? There's a difference between the first and second term plus the difference between the second and third term. So that's 2 differences, right? Very good. So a plus 2d. What do you suppose the next one would be? A plus 3d, which I don't know if I put that on the slide. I did put that on the slide, okay? Now, that's just the pattern of it, and it would just continue on. So is there anything we can observe about that before we look at the second version? Each time each new number in the pattern, what happens to that number there, the actual number, the 2, the 3? How does it relate to where you're at in the sequence? It's a hard question to ask. I'm trying to ask you to read my minds at the moment.
And minus 1.
Yeah, it's whatever number, whatever term you're on, minus 1, right? So, for example, this one is the third term, right? Third term, but it's only a 2d. So third term, 3 minus 1 is 2. This one here is the fourth term, and the 3 is the fourth term, minus 1. Okay, it's always n minus 1. Okay, very good. All right, so now let's take a look at basically a general formula rather than like the first one, the pattern there or the values. We're just listing them out one at a time. We don't want to do that. We can do that, and that can be useful in certain circumstances. But let's look at how we could do a formula here. So any thoughts of what a formula for this might look like? What we're looking for is the nth. We want to know what is the nth term, right? What is the first term? What is the second term? What is the third term? So typically we'll use term and little n, subscript. I believe the book uses capital A instead of a T. So if you see that in the book, and maybe even some of your homework problems will have a capital A instead of a T, but it's the same thing, right? It doesn't matter what variable you use. So term number n is equal to what? How can we generalize this in some sort of formula? Can we think of how that might go?
N minus 1d.
There you go, very good. A plus n minus 1 times d. Let's just make sure before I put that on the screen why that's true. We already just talked about that, right? Where whatever one you're on, like this is the third term, well, this number right here is literally just n minus 1, right? And then it's always times d, it's always times that difference, okay? So the first part of it, well, it's always going to be a, whatever the first term is, and your sequence will always be defined in terms of the first term, pardon the little wordplay there, and then plus some number times d, right? What number? It's n minus 1, right? And n being whatever term you're on. Does that make sense? So plug in some numbers there real quick. If I wanted to know the third term, t sub 3, that would equal 1, which is a, plus n minus 1, which is 2, times the difference, which is 4 in this case, and that would give us the number 9. Another way we can do it is everybody's favorite thing, recursion, right? I'm assuming since you've probably taken 1410, you are familiar with recursion. We're going to look at a recursive sequence a little bit later today, and we will spend some time in a future lecture talking about recursion in more depth. But for now, who wants to give me the big picture? What is recursion? Yeah, it's a function that just calls itself, right? It returns as part of the value, as the return value, another call to itself, right? So again, we're looking for the same thing. We want to know what t sub n is. What's the one thing you always have to know when you're writing a recursive function? Well, there's more than one thing, but there's like the major thing you start with. The base case, right? You have to know when to exit out of the function, or else you have an infinite loop. This is the same thing. It's exactly the same thing. So, or not an infinite loop, but an infinite recursion, which is worse in some cases. So our base case, we're going to start again with t sub 1, right? The first letter in the first number in the sequence. What is the first number in the sequence? Or, generally speaking, A, right? T1 is equal to A, right? Very good. So now we want to look at what's T sub n. Well, what is T sub n? And think about recursion now. You're going to recall, like think of T as a function now. What would T sub n be? So we have T sub n minus 1. So what does that mean? If I'm looking for the fourth term, well, then I have to know what the third term is before I can do anything, right? And that makes some sense, right? If I want to know, using this recursive formula right here, if I want to know this term, I have to know this term and then just add 4 to it, right? That's exactly what's happening here. If I want to know, let's say, the fourth term, which is not written here, well, I need to know the third term, 9, plus my difference, 4. That'll give me the next term. So in a recursive function, you have to know the previous term. And that's how recursion works, okay? And again, we'll talk a little bit more about that later. But does that make sense how that recursive formula is working there? Now, a recursive formula can be very useful in proving that you really do have an arithmetic progression. This can be useful in doing a little mini quasi-proof, okay? So here's how this proof might look. We want this to be true. Take a look at that on the screen there. Okay, for all n, we want T sub n minus T sub n minus 1 to equal the difference. Would you agree that that needs to be true? Okay, does everybody understand why that's the case? Does that make sense? All right, and again, you can, and I'm missing a parenthesis there. You guys see it? I'm short one parenthesis, sorry about that. There should be an extra parenthesis right here. Sorry about that. I'm not gonna fix it, deal with it. All right, so, but that, you guys agree that should be true, right? Okay. So in other words, we're looking for this. T2 minus T1, term 2 minus term 1, should equal term 3 minus term 2, which should equal the difference, right? So if I subtract term 2 and I subtract term 1 from it, that gives me 4. If I subtract, I take the third term and I subtract the second term, that also gives me 4, which is the difference. And remember, when you're doing an arithmetic progression, you only need 3 digits to prove the pattern, right? You only need 3 digits. You don't need an infinite set of digits. This implies infinity, 1, 5, 9, infinity, dot, 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 through infinity, but I don't need that many terms to do the proof. I just need 3 terms. And 3 terms. I was holding up 4 fingers there, sorry. So I only need 3 terms. And if that little math there holds true, then we're good. And it's an arithmetic progression, and we know what the pattern is, and we know what we need to know to solve problems relating to it, which we'll look at some of those examples a little bit later. Okay, there's one last thing we want to know about here, and that is that n is always an element of positive integers. Why is that?
It's the nth term, you can't have a negative.
Yeah, so that t sub n, you can have a t sub 1, the first term, the second term, the third term, but what's the 2.5 term, right? There's no such thing. What's the negative 4th term, right? That's not a thing. So we're dealing, you could argue that n is an element of the natural numbers, except for the fact that 0 is considered a natural number and you don't have a 0th term, right? Okay. There are 3 ways here that we're representing an arithmetic progression. In a minute, we're going to get to another type of progression, and we're going to look at 3 ways to represent that, which are the same, pattern, general, and recursion, but the formulas are different, obviously. Okay, what questions do we have about this? Yeah?
General formula more, or we use the recursive formula in street math?
Yeah. Did you say street math? What did you say? Oh, discrete math. Like, dude, what is street math, man? Like, you're out on the streets hammering out some equations, man.
Street smarts or something.
That's right. Well, I'm thinking like street magic, like David Blaine, right? You know, this whole vibe of this. Yeah, that's funny. Street math. I like it. So yeah, the first one, the pattern was just, the only reason I showed you the pattern, that number 1, was because if you can see, we were kind of baby stepping our way to derive the formula, basically. If I showed you the sequence 1, 5, 9, we can look at that in general terms as A, comma, A plus D, comma, A plus 2D, and we could see this pattern. With that pattern, we could sort of figure out what the formulas might be. So it was just me sort of helping you derive those formulas. I almost used a term that is a Navy term, which was, I was going to say, we use that pattern to help us nuke out the formula. In the Navy, the field I was in was a nuclear mechanic, and that's sort of the engineering field, and our nickname, we were nukes, that was our nickname, and they always made fun of us for being engineers, so they'd say, don't nuke it. And it didn't mean don't drop a bomb on it, that meant don't overthink it, basically. And so oftentimes we'll say nuke it out, which means figure it out or think through it. And that's just an old term that I haven't thought about for over 20 years. Anyway, now you know a little bit more about me and the Navy. Go Navy. So any questions? Other than that, good one there, Craig. Thank you very much for that. All right. Let's take a look at some examples here of how these formulas can be useful to us. I've removed some of the other stuff from the table there and just left those three things. List the four terms for A equals 9 and D equals 3, right? You'll always have to have those numbers if you're going to be able to establish a pattern, right? If you're going to create a pattern, you have to define those values. So if you're watching the video, pause the video and take a minute and see if you can see if you can nuke it out, figure those out. What are the first four terms for A equals 9, D equals 3? Anybody? What's the first term? 9, right? That's a given, okay? What's the second term?
12.
Yeah, it's 9 plus 3, right? 12. And the next term? 15 and? Yeah, very good, okay? So we could, in that case, we just kind of use the pattern. You didn't even need the formula, right? You could just use the pattern to think through it and bam, there you go, okay? All right, pause the video and ask yourself, what is the 42nd term? Or you guys can play right now. Why 42, by the way? Come on. Anyone?
Some idea of the universe.
Yeah, it's the meaning of life, universe, and everything. Yeah, it's Hitchhiker's Guide to the Galaxy. All right, what is the 42nd term? How would we even figure that out?
42 times.
Yeah, we have a formula for that, right? Now, there's two formulas we could potentially use there. Let's take a look at the third formula first, okay? Why would the third formula be bad? Because we're not a computer. Good answer. Yeah. Yeah, because in order for the third formula to work, I'd have to know what the 41st term is. And if I want to know the 41st, I have to know the 40th. And if I want to know that, I have to know the 39th, and so on and so forth. And the whole point is, a computer could figure that out in just a matter of seconds, depending on how complex the calculation was. But there's a better formula, and that's the second one there. And it's pretty simple, right? We just plug T sub 42, so we're going to use that formula right there. And that's what it would look like, right? T sub 42 is equal to 9, because that's A, plus n minus 1, which is 42 minus 1, times 3. Agreed that would give us the answer, right? So the 42nd term is 132 if you do the math, okay? There are some famous sequences we'll briefly touch on some of them. We're not really going to go into depth, but I'm going to give you a good resource where you can learn more about them. But sometimes it can be useful to figure out what is the nth term in a sequence. That can be useful, okay? All right. So next one. Again, pause the video and take a minute to answer this question, which is, prove that the following sequence is an arithmetic progression: 88, 83, 78. How would we go about proving that?
Use the T2 minus T1 equals T3 minus T2.
Very good. Use that simple proof, right? Where we subtract we take the second term, subtract the first term, see if it equals the third term minus the second term, right? So let's take a look at what that would look like. That's the formula right there. That's our basic proof formula. T2 minus T1 it should equal, this is what you're hoping is true. It may not be true, but we'll see. Okay, T2 minus T1 is equal to T3 minus T2. It's like the Terminator movies, man. Okay, equals D. All right. So the first one, 2 minus 1, term 2 minus term 1 is 83 minus 88, which is negative 5. And then the third term minus the second term is also negative 5. They both equal each other, and therefore that is the difference. Therefore it is, this is the part where you guys as a group say arithmetic progression, right? I've been trying to start a cult with you guys, to get you guys to chant these mathematical statements, and you won't do it, man. All right, any questions about that basic idea? We good? Okay. All right, let's take a look at geometric progressions. This is another type of progression. GPs is another common name for them. Let's take a look at the variables involved, and we're going to use this sequence right here, 5, 25, and then 125. That's the correct sequence, right? All right, so the variables, very similar. The first term, these progressions are always in terms of the first term. That's always the thing that you need to know, right? So we're going to use A again, just like before, for the first term. And then rather than doing a D for difference, we're going to do R for ratio, okay? R is going to represent the ratio. And then the ratio is an element of all rational numbers, the set of all rational numbers. That's what the Q stands for, okay? So we got the big picture on the variables. We good there? Okay. All right, now let's take a look at the pattern for this. Again, it's much like we have over here. We're going to start with the first term being A, right? So that we're going to put an A right here. That'll be our first term. And then the next term is going to be not A plus D, but it'll be A in something related to that ratio, right? So first term, A. What would the second term be? What is our ratio in this particular case? It's 5, right? Okay, so if I divide each one by 5, I'm going to end up with the previous number, right? If I multiply it by 5, I'm going to end up with the next number. Okay, so what would my second term be in terms of A and R? Yeah, it's just A times R, right? If in this case, so A is 5 in this case, and R is also 5 coincidentally, okay? So that's A times R. That gives us our second term. What would the next term be? Yeah, it's A times, 2 R's, right? Another R, a second R. It's just times that ratio again, okay? And then the fourth term, if we had one that we wanted to show, yeah, AR3 and then AR4 and so on and so forth. So now, using that information, we can, again, derive sort of a general formula, right? We can see this pattern here. What pattern do we see there? Again, in terms of R and its power that it's being taken to, how does it relate to which term we're on? Yeah, it's raised to the power of the nth term minus 1, not the n minus 1, right? Not the nth term, but just n. Very good. So in that case, then T sub n will be equal to A times R raised to whatever number we're on minus 1, right? So A times R to the n minus 1. Make sense? All right, plug in a number there. Take the third term, T sub n. Okay, so that's going to be A times R to the n minus 3, the n minus 1, which is 2, right? So T sub 3 is equal to A, which is 5, times R, which is also 5, squared. Well, 5 times R squared, in other words, 5 times 25 is 125, right? So this will work plugging things in. And this will give us, if I want to know the 10th term, T sub n, plug it in and we'll get the answer, okay? That make sense? All right, now let's look at a recursive version of that. And again, what do we always need with recursion? Base case, which is? What's our base case here? Yeah, 5 or A, right? T sub 1 is going to be A. Okay, very good. Now, what T sub n is equal to, again, in recursive terms, what would this be? Yeah, so we know that there's going to be a T sub n in there somewhere, right? A T sub n minus 1, because typically with recursion, you're looking at the previous term. Well, the previous term is always T sub n minus 1, right? If you're on the 5th term, the previous term is the 4th term, which is n minus 1. Make sense? Okay. So it's T sub n minus 1. That's always going to be there. Then times what? Just multiply that by the ratio and we're good, right? Think about that for just a minute. If I'm on the second term, all I have to do is multiply the first term by the ratio, which is 5 in this case. If I want to know the third term, I just have to multiply the second term by the ratio, right? Multiply that second term by 5 and I'll get my answer, right? So that's your final recursive equation there. Everybody see that? I know this is like wordy, tricky stuff. And you may be like, well, who cares about sequences? They're important, okay? And it's a data structure, right? It's a way to represent some data, and it can be, there's some really cool sequences. We'll look at one of them in particular in a few minutes, okay? How are we feeling so far, though? Good? Questions? Okay, we want to prove that this is true, so using the recursive function, you can prove that it's true, and this is what we want to prove. But look at that closely, all right? Okay, this is saying for all n, t sub n divided by t sub n minus 1, that looks like a dash, but that's actually a minus there, just the way the subscripting works on there, it comes out funny. But t sub n divided by t sub n minus 1, in other words, some term divided by the term before it should equal the ratio, right? In other words, 125 divided by 25 should equal the ratio. 25 divided by 5 should equal the ratio, right? We want to prove that's true. Well, what could I do, sort of remembering this little deal we did over here, what could I do similarly in terms of term 2, term 3, term 1, or whatever? What kind of a formula could I do right there?
2 divided by term 1.
Yeah, term 2 divided by term 1 should be equal to term 3 divided by term 2, yeah? Term 2 divided by term 1 equals term 3 divided by term 2, which should equal the ratio, okay? Does that make sense?
How does the recursion for geometric work again? So you have your previous,
Yes.
your previous t
Yep.
or a times by r. How is that?
So ask the question again, sorry.
How is that? Because I guess I can see like how, what is it? Because T1 is A, right?
Yeah,
So it's A, like, I'm talking about arithmetic now. A minus whatever in the previous,
oh, you're talking about arithmetic?
I mean, I'm giving the example of arithmetic, but I'm
Okay.
trying to see how that works with geometric. Even though it's not the same, but how is that?
Right, so what's happening here, so look at these terms here. We happen to know what these three terms are, okay? But what would be the what would be the fourth term, just mathematically, what would it be?
Would be, was it R cubed?
Well, no, but just, just forget the equation, the A's and the R's, what would the next number be?
Times 125 times 5.
Yeah, 125 times the ratio, right? So I want to know this number right here, that's t sub 4, right? So I would ask the question, what is t sub 4? Well, it's t sub 4 minus 1, which is 3, which is the third term, right? So it's this term, the third term, times the ratio, right? That makes sense? Yeah. So anywhere down the line, so now the catch with that is, well, what's t sub n minus 1? Well, you can see it on the screen, it's 125, but in order to know that number, I have to know t sub n minus 1, right? And I have to keep, that's where the recursion comes in. So in order to know the third term, I have to know the second term. In order to know the second term, I gotta know the first term. And so with recursion, this would have to, if I wanted to know like the 50th term, I'm gonna have to call that function recursively 49 times or 50 times or whatever, right? Yeah, does that make sense though? Is that cleared up? Yep. All right. So again, these are the three ways that we can represent an arithmetic or a geometric progression, 1, 2, or 3, okay? A pattern, general, or a recursive function, all right? And again, there's our little proofs down there that we want, and in all cases, for n, it will be a set of the positive integers right there, okay? It'll be in the set, an element of it. Questions? How do we feel about that? Doing all right? Let's take a look at a couple exercises here. We want to find the first four terms where a is 4 and the ratio is 4, okay? So pause the video, and see if you can figure that out. I could use the pattern, right? I mean, we know the first term is, what is it? 4. It's 4, right? What's the second term? 16, right? Because it's a times the ratio. What's the third term?
64.
Yeah, we just keep multiplying by 4, right? So we just using that pattern, we can figure out what the first four terms are. It'll be 4, 16, 64, 256, right? Just multiplying it out each time. Pretty easy, right? What's the 42nd term? First of all, how big is it going to be? It's going to be ginormous, right? Okay. But what can we do to figure that out? Again, pause the video, see if you can give it a shot. use the explicit formula there, or the general, good, I copied your words, the general formula, very good, okay? So use that formula, and let's just plug it in. T sub n equals A times R to the 42 minus 1th power, right? Like that. Don't bother doing the math, all right? Who knows what it's gonna come out to be? Yeah.
How is this any different than just a to the n?
Oh, I see what you're saying.
Like,
In this case, coincidentally, it is not different.
okay, but there are.
Yeah, so the question was, how is this different from a to the n? In this case, that it is a to the n, but what if your first term was 5?
Oh, because
Right.
R can be different.
Yeah, or if your ratio is different. This case, just coincidentally, the first number and the ratio are the same. Our last problem, we had that same thing too. The first number and the ratio were the same, but that will definitely not always be the case. Yeah, good point. All right, let's take a look at a couple of exercises here, and just make sure we've got this sort of nailed down and we understand it before we move on to the next phase of this. All right. My intent here is we're pardon the pun here, but we're progressing in our knowledge of models to represent data, right? We started off with sets a couple days ago, 2 or 3 lectures ago or whatever, and we have the big picture that a set is just a group of stuff. Then we move on to this idea of a sequence, that it's a specific order of that group of stuff. And a sequence can only be represented in a specific order. If it's a different order, it's a different sequence, right? That's what the word sequential means, right? It's in a specific order. And so now we're just trying to understand, how can we represent them? What are some patterns that we can use, some formulas? How can we represent them so if we need to use them in the future, we can represent them easily? Because this sequence, if I were to put a dot, dot, dot at the end of it, it's an infinite sequence. It can go on forever. Well, we can't write infinity, right? We can't write infinite numbers. So we need concise ways to represent these things. So this is why we study these patterns. And then there are things that sequences are really cool when you start studying them. And I'm going to give you a resource a little bit later. It's oeis.org. It's the Online Encyclopedia of Integer Sequences. That's what that stands for. And I think it's .org. Really cool website. Anyway, we'll get to that in a few minutes though. So let's start with this sequence right here. 5, 8, 11, 14, 17. Okay, what's the pattern here? What's A? What's D? Yeah, A is 5. The first term is 5, and the difference is 3, right? 5 plus 3 is 8. 8 plus 3 is 11. 11 plus 3 is 14. So on and so forth, right? Pretty straightforward. Okay. Does the pattern hold? And by what do I mean by that? I'm asking, does A, then comma A plus D, then comma A plus 2D, does that hold? Does that pattern hold? Yeah, it does, okay? If you look at that, plug in the numbers, you'll find that it holds. Feel free to take time on your own to do that. And I plugged in a few numbers there, and you can see that it will actually pan out, okay? Make sense? Just want to make sure that these are sinking in, okay? All right, does the formula hold? What's our formula again? For an arithmetic progression, an AP? T sub n equals A plus n minus 1 times D. Very good, okay? Does that formula hold true? Plug in some numbers and you will find, take the first one. T sub 1 is equal to 5, which is the first term, right? Plus 0 times 3. Why is it 0 times 3?
1 minus 1.
Yeah, 1 minus 1. And then 3 is what? D, yeah. So this, just to make sure we're clear here, this, the nth term, the n at the moment is 1, right? It's 1, right? So 1 minus 1 is 0. Multiply that by the difference of 3, and 0 times 3, of course, is 0. You add that to 5, and you get the final number 5. So the first term is 5. Plug in the next one, and you'll see that the pattern holds. Feel free to pause the video or to walk through these and make sure you follow the math correctly. But you'll see that each one of these terms, it will hold all the way through, okay? You plug those in. Feel okay about that? Questions? All right, let's take a look at another sequence here, okay? Another progression, right? A progression could be an arithmetic or it could be a geometric, right? But they're progressions. Okay, so what do we have here? What's the pattern here? What kind is it, arithmetic or geometric? It's geometric, right? Okay, so what's the pattern? What's the A, what's the R? 2, and again, coincidentally, also 2. That is a coincidence. All 3 times we've had that happen. That is a coincidence. The ratio, I mean, that could just as easily, I could have made everything 3 could have been the ratio, right? That's just a coincidence that they happen to be the same. But yeah, they are both the same, okay, in this case. All right, so arguably in this case, if you wanted to, you could make the pattern like we were talking about earlier. You could just make it a to the n. If in this pattern, that would be a legitimate way to represent this, right? But to be more general, to fit all geometric progressions, you want to go with the regular formula, okay? So does this pattern hold, right? In other words, does that hold? Is the first term a, is the second term a times r, is the third term a times r squared? Is that true? Yeah, plug in the numbers and you'll see that it is true, okay? The first term is 2, second term is a times r, which is 2 times 2, which is 4, so on and so forth, okay? Does the formula hold? What's the formula? Right there. Does that hold? And again, as we pointed out a second ago, due to the fact that the ratio is the same as the first number, we could get away with doing a to the n in this particular case, but we want to stick with the general formula that works for all geometric progressions. And does it hold? Yep, just plug in a couple there. T sub 1 is equal to 2, which is our a, times 2 to the 1 minus 1, which is 2 to the 0. What's 2 to the 0? What's anything to the 0? 1. What's 2 times 1? 2, right? Plugging in all the numbers again, you will see that this will work every time, okay? How do we feel? Questions? To the whiteboards. All right, let's take a look at these, see what we get here. First one's pretty straightforward, right? This is our pattern for an arithmetic progression, and you can quickly see that it is an arithmetic progression because you can just quickly see there's a common difference, right? When you're looking at these kind of problems, first thing you want to do, see is there a common difference. If there's not, see if there's a common ratio, right? If there's not, you have a third thing on your hands, right? Which we'll talk about in a minute, okay? Looking here though, our formula is a plus n minus 1d for, well, clearly we do have a common difference, right? What's the a in this particular case? And what's the common difference? Negative 7, right? Very good. Because it's the second term minus the first term, or the third minus the second, which will give us negative. So the formula in this case is the first term, a, 23, plus n minus 1, whichever term you're on, times negative 7. Good? I think everybody got that. And that, of course, is an arithmetic progression, right? Does that hold true? And it does hold true, and we'll see it's an AP. Easy enough. I think we're all okay there. All right, next up. Does the next one have a common difference? That's the first thing we should look for. Does it have a common difference? It does not. Does it have a common ratio? It does. All right, so it has a common ratio. Therefore, we're going to be using this one. So with our pattern of a times r to the n minus 1, we plug in the numbers. Again, the a is 1/3, and then the ratio is negative 1/2, right? If I multiply 1/3 times negative 1/2, I'm going to get negative 1/6. If I multiply that again, raise that to the n minus 1. So what is 1/2 to the n minus 1 for the first term? Right, yeah, n minus 1 is 0 and for the first term, right? So that's negative 1/2 to the 0th power. What does that come to? 1. 1/3 times 1 is? Good, it's 1/3. All right, let's try it again. Just make sure that we're seeing the pattern here. So for the second term, so 2 minus 1 for an n minus 1, that's 2 minus 1 is 1. Okay, and then what is negative 1/2 to the first power? Negative 1/2. You multiply that by 1/3 and you get negative 1/6, right? So plug in the numbers and you'll see that it follows. It does hold, okay? So what kind of progression is this? So does this hold true? If that holds true, then it is geometric. And if you do the math, you'll see that it will hold true, okay? So it's a geometric progression. All right, questions about those two? Those two are pretty straightforward, I think, okay? The third one. This one's a little trickier, okay? This one is trickier. I'll spoil the final answer for you right now. It's neither arithmetic nor geometric. It's neither of the two, okay? AP and GP are not the only two type of progressions, okay? This is just a who knows what you want to call this kind of progression. There's probably a name for it, but there is a pattern still, though. So think about this. Each one of these terms, this is the first term, that is the second term, third, fourth, fifth term, right? So basically the question I'm asking when I want you to show me a formula or a pattern is in terms of n, right? T sub 1, T sub 2, T sub 3. What can I do to the number 1? In fact, I'm going to open up a notepad here, and so we can look at this a little bit more clearly, okay? 4, comma, 7, comma, 12, 19, 28. 12, 19, 28. All right, so what I'm telling you is that that's the first term, that's the second term, that's the third term, that's the fourth term, that's the fifth term. You guys agree with that? Okay, what if I wanted to derive a formula in terms of n, right? N is 1 or 2 or 3 or 4 or 5. The question I'm basically asking is what can I do to this number to give me that number? What can I do to that number, which is the same thing that I did to this number, that would give me this? And can I apply that same formula to the number 3 and get 12? And can I apply that same formula to the number 4 and get 19, and so forth? Does that make sense? That's what I'm asking you to do, okay? So what can we do to the number 1 that would give us 4? What are some things you could do? You could just add 3 to it, right? Right, I could just add 3 to the number 1 and get 4. So let's try that with term 2. What happens if I add 3 to term 2? I get, or to the number 2, I get 5. That doesn't hold, right? So adding 3 to it doesn't work. What else could I do? What could I do to take to 1 and get a 4? Mathematically. What's that? I could multiply by 4. So I could say, in other words, we're saying n times 4, right? So first time it'd be 1 times 4. That does give me 4. Okay. Second time it would be 2 times 4, but it gives me 8. Doesn't quite work, right? But if I multiply 4 times the third term, it does give me 12. So it's like it sometimes works, sometimes doesn't. So that's not quite the right formula, right? This is like a trial and error thing, right? What else could I do to n, to 1 or to 2 or to 3 that will give me the number? What happens if I square n? What happens if I square n? Let's look at those for just a minute. What's 1 squared? Oops. What's 2 squared? 4. 3 squared? 9. 4 squared? 5 squared? Okay. Now these new numbers here. Compare them to the number I'm trying to derive. They're all 3 away from the number I'm looking for. So if I were to do n squared plus 3, I could apply that to any term, and that according to these 5 digits here, the pattern will hold. Right? Does that make sense? Now, how do you get to that? Trial and error. Right? You just got to look at it and think about it. And what can I do mathematically to the n, to the nth term, to just the n itself, right? So it's not just an intuitive bam, there it is. It takes a little bit of dinking around and kind of nuking and out, as we talked about earlier, right? Okay. Does this pattern here hold? And the answer is no, it doesn't. We've already established that. That would be for a geometric progression. Neither of those two patterns hold. The a plus n minus 1 times d or the a to the n minus 1, neither of those hold. It's neither arithmetic or geometric, okay? What we found is that this formula here, however, does work. T sub n is equal to n squared plus 3. That will give us that pattern. So that little formula is a way to represent this sequence. Feel okay about that? Okay, so the part of what's important about this class, especially as a computer scientist, is recognizing patterns. That is a huge deal, recognizing patterns. That can be very useful when writing code, when dealing with data structures, when writing algorithms. It's a very useful skill to have, being able to solve logic problems and puzzles and to be able to recognize patterns, okay? So this kind of stuff can be useful for that, but also sequences are useful just in and of themselves, yeah.
So when it's neither, you don't need to include an A1 term.
Not necessarily, depending on what, yeah, in this case, we weren't doing the pattern. If I were drawing the pattern out, then we might. And if we were gonna write a recursive function for this, we would need the A term, because the A term is your base case.
Right.
So, and there's always an A term, right? It's just whatever's the first one.
Be one.
Yeah, in this case, it would be 4. So in this particular formula, it's not necessary, but in there, you could, depending on what you were doing with it, yeah. Any questions? What do we have here? I don't think that 6 is supposed to be there. To the code. No, to the whiteboards. Dang it, I ruined it. Oh, we're gonna do that again. All right, ready? To the whiteboards.